Welcome to Flink Forward Asia 2024.
Now, we are directly to begin our first presentation this afternoon about Apache Flink 101, which will be presenting by Mr. Xintong Song, Alibaba Cloud Software Engineer Staff Apache Flink PMC. Boleh kita berikan tepuk tangan untuk Mr. Xintong Song. Welcome back, sir.
Thank you. Hello, good afternoon. It's me again, Xintong from Alibaba Cloud Flink team, and I'm a Flink PMC member. So, given that this is the first time that we have this kind of technical event around Apache Flink in Indonesia, so I'd like to provide an overview introduction to this project. Sorry, it's not working? Okay. Okay, so I'd like to start with this question. So what is Apache Flink? Well, this is a screenshot from our project website. It says that Apache Flink is a framework and distributed processing engine for stateful computations over unbounded and bounded data streams. Well, here, the key information are highlighted as a title, the stateful computations over data streams. So let's keep these two keywords in mind, the stateful computation and the data streams. Those are the key concepts to understand Apache Flink, and I will come to them later. Well, the next question is, what can Apache Flink do? Well, Apache Flink as a stream processing engine, it is widely used in various industries, including the social network, e-commerce, finance, transportation, energy, game, media, telecom, logistics, and manufacturing, pretty much everything. And within those industries, Flink are deeply applied in various technical scenarios. For example, the real-time dashboard, the data integration, lakehouse analytics, personalized recommendation, and also risk control. Well, the new use cases and scenarios keep emerging. Then, how is the stream processing performed in Flink? Well, to answer this question, I'd like to come to this most fundamental concept in Flink, that's the data stream. Well, Flink models the data to be processed as a stream of record, or data records. The record can be any data. It can be, for example, the credit card transactions, or some user behavior, user actions on a website or on a mobile application. It can be literally anything. Well, such kind of records are generated, collected, and processed in a stream. And the data stream can be further categorized into two kinds. That's the unbounded stream and bounded stream. Bounded data stream has a determined start and end. That means the amount of the data is fixed. So the framework will stop processing when all the data has been finished processed. Well, on the other hand, the unbounded stream does not have a determined end. So that means the amount of data keeps growing as new data being generated and collected. So the framework won't stop processing. Even though all the existing data have been processed, the framework will still waiting for new data to be generated and collected. So that's the unbounded stream. So bounded stream is kind of corresponding to the batch processing. Well, in the data stream model, the batch processing is only a special case of the unbounded stream, where of the stream processing where the data stream has an end. So this is why we say that Flink is a stream batch unified processing engine that can be used not only for stream processing, but also for batch processing. Well, let's take a look at an example. So here is an example of the work on the example. This is basically the hello world of the data streaming, data processing world. Well, we start with a Java program. Here we define a data stream called text. Well, this is a data stream that is reading data from a Kafka source. And then we convert this text data stream into another data stream called count. Well, to do that, we first use a flat map function called tokenizer. It will generate the tokens from the text. And the output of the tokenizer are a stream of tuples, where each tuple consists of the token itself and also a number 1. And then we convert this data stream into a keyed stream. Well, keyed stream is a special kind of data stream which guarantees that all the data with the same key will be processed at one place. So here we use the token itself as the key. And after converting it into a keyed stream, we will calculate, we will add up for each key, we will add up all the tuples, the field 1. So we know that the field 1 is always, of the tuples are always number 1. So the counting result will represent how many times each token has appeared. After converting this count stream, we send these results to another sink. Here we just use a print sink, which will simply just print all the results. So this is a Java program. And when this program gets executed, it will be compiled into a directed a sync-like graph, a DAG. And in this DAG, each vertex represents an operation, and the edges are representing the data stream between the operations. So in our example, we can see that there's 4 operators, the source operator and 2 transformation operators, and also a sync operator. Well, the DAG we see in the previous slides was called a logical plan. And now we need to optimize it into a physical plan for execution. So the first step is, to do that, the first step is operator chaining. Operator chaining is that we chain multiple operators together so they are executed in the same thread. And the chained operator is also called as tasks. And then we expand this graph into a distributed version. So we separate each task into subtasks, where all the subtasks of the same task have the exactly same processing logic, except for they are processing different partition of the data stream. So this is what we call the physical plan. Well, a Flink cluster consists of 2 kinds of processes. That's the job manager and the task manager. The job manager is centralized. It has 1 or multiple job masters, and each job master corresponding to 1 job that is running in this cluster. And there's also some cluster level components, for example, the dispatcher, the REST server, and the resource managers. And task manager is where the data is actually being processed. A task manager contains some task slots, and each task slot represents a piece of computing resources, such as CPU, memories, those kind of things. And a task slot is a minimum resource scheduling unit in Flink. So when we want to execute a job, we submit the job with a client, submit the job to the job manager, and the job manager will create a new job master for this job. The job master will be executing the user program and compile the logical plan and the physical plan that we just mentioned. And then it will deploy the tasks, actually the subtasks from the physical plan. It will deploy those tasks into the task manager slots for execution. So this is how, in general, how stream processing is done in Flink. And the details might vary a bit because Flink has many different deployment modes. Well, here is a component stack of Flink. And the Java program we see in the previous word count example corresponds to the blue and the datastream API. So it's programmed with the datastream API. Datastream API is a low-level API of Flink. It's corresponding to the stream processing model. And on top of the datastream API, Flink also provides many different API sets, high-level APIs and libraries. For example, we have SQL, which allows you to define your data processing logics just like using a database. And we also have Table API. Table API is a relational API which is similar to the datastream. Which is similar to the SQL in terms of the semantics and in terms of the expressiveness. But the difference is that the Table API are in Java, so you can define some complex logics which can hardly be expressed with SQL. And we also have the data integration framework, Flink CDC, which is used for synchronizing data across different storages. And we have PyFlink, which is a Python API of Flink. And we have FlinkML, the machine learning libraries. And we also have a library called CEP. This stands for the complex event processing. This is used a lot in the real-time fraud detection. And Flink also provides massive connectors so that you can read data to and from and write data to different storages. So we support streaming storages like Kafka, like Flume and RabbitMQ. We also support data lake formats like Pymon, Asperg, and of course databases and files just in local or remote file systems. Well, all these workloads are running on a unified runtime, distributed runtime, and that can be launched, that can be deployed in different various environments and clusters such as Kubernetes, Yarn, and standalone machines. Well, now we have some basic understanding of Flink. Then that bring us to the next question. What makes Flink stand out among all the streaming processing systems? So we know that Flink is not the only stream processing engine. For example, we also have Storm, we also have Spark Streaming, but Flink is definitely the best state-of-art stream processor. And why is that? Why is Flink different from others? Well, to answer these questions, we need to look into some key challenges of stream processing and how Flink solves these problems. So the first thing we want to look into is stateful computation. Remember the keyword that we mentioned before? Okay, stateful computation is a pattern of computation that, given the input and the original state, we are computing for the output and also generating a new state. And the new state will be used for future computations. So in our word count example, we have a sum operator which counts how many times each token have appeared. And in order to do that, the sum operator needs to remember how many times it has seen each token. And this is called the state. Well, when the new input arrives, the operator will look into the state, looking for the corresponding state, and it will combine the input and the state together to calculate for a new count. And the calculated result will be sent to the output, and it will also be used for updating the state. So this is for stateful computation. But what is the challenge here? What is the challenge here? Well, the challenge here stay with fault tolerance. So imagine this. If there's a failure happen and all the states are lost, then what can we do with it? Well, we can say that we just we just resume the computing, resume the processing from where we left. But that would mean that we start counting from after the failure. Because if now we have a new, we have another hello input, and we look into the state, because the state has been lost, then we will, the operator will think that this is the first time it sees this token. So it will get to the incorrect output, which means it will output hello 1. Yep. But that's incorrect. Well, we can do in another way. Let's say we can try to reprocess the entire processing. We can start from the very beginning and to correctly build the state again. But imagine that we are dealing with an unbounded stream. So that means your job may have been running for days, weeks, or even months. So it's just too expensive, too time-consuming. It's just impossible to just reprocess all the data. So how does Flink solve this problem? Well, the answer is checkpoint. Flink uses checkpoint to solve this fault-tolerant problem. The idea is that we periodically make some checkpoints, and when making a checkpoint, we just persist the operator state to some durable storage. Well, here in this example, we have three input records, and the corresponding states before processing each record is 2, 3, and 4. That will give us the output result 3, 4, and 5. And then we make a checkpoint at the second input record. Then the corresponding state would be 3. This is a state that being persisted in the checkpoint. And then when a failure happened at this time, we need to restore from the latest checkpoint. And that will give us the state, will reset our state to 3, and we need to replay from where the checkpoint is made. That means we want to replay the last 2 input records. So in this way, it will give us the correct result. That is, the final count is 5. Well, this is the fault tolerance. But the problem here is that how do we make these two things consistent? How do we make the restore of the state and the replay of the input consistent? Because we need to make sure that we are replaying the input from where we restore the state from. For example, in this example, we are restoring the state from state 2, which is a state before we process input 2. That means we need to replace the input from input 2. Only in this way we can make sure that we are processing each record exactly once, and this is called the exactly once consistency. But if we are replaying from another position, for example, if we are replaying from input 1, that means we are processing input 2 twice, because the state 2 is that means we are processing input 1 twice, because state 2 is a state that after we already processed input 1. And or if we replace the input from input 3, then we are skipping input 2. Input 2 is never processed. So this is called the at most once. And how does Flink guarantees the exactly once semantics? Because we know that the input of the operator are either read from source from an external system, or it's output from upstream operators. Then how do we make sure that they are replayed from exactly where the checkpoint is made? Well, Flink's checkpointing mechanism uses these checkpoint barriers. The idea is to insert some barriers into the data streams, and a barrier marks the position where a position in the stream where the checkpoint should be made. And by propagating the barriers through along with the data stream and through all the operators, we can make sure that all the operators are making the checkpoint at at the same position in the data stream. And when there's multiple inputs, we need to align the barriers. That means we can guarantee that no data behind the barrier can be processed before all the data after before the barrier is finished. So in this way, we can make sure that when restoring from the checkpoint, the output of the upstream operators are exactly those input that need to be replayed for the downstream operators. So the whole workflow looks like this. When we start a checkpoint, the job master will tell all the source operators to insert the barrier into the data stream. And the source operators will also record the current position in the stream. This is for replaying the input from external storages. And when the downstream operators receive the barriers, they will align the barriers and process their own states, if any, and then they will forward the barrier to the downstream. And when all the operators in the job has finished processing their states, and when the sink has finished writing the data to the writing all the data before the barriers to the external system, the checkpoint is considered finished. Sorry. So this is about Flink's fault tolerance system. Well, another challenge of Flink of stream processing is time-based processing. Well, time-based processing is quite common in especially the real-time processing area. And before we dive into that, I want to clarify some concepts. So Flink supports two different notions of time. That is processing time and event time. Processing time is just the machine time when the data is being processed by the operator. Well, event time is the inherent time of event of the data. For example, it can be the time where when the data is being generated, or it can be the time when certain event happened. Well, dealing with processing time is quite straightforward. It's just like you would do in any Java application. You can check for the system clock, and you can just register some kind of timer which will notify you when the certain time is reached. But event time handling is not that straightforward. The problem is, how do we measure event time? How do we know what time is it now? So some people would say that could be straightforward because we can just look into the data, and if we see a new timestamp, then we know that the event time has progressed. But the problem is that in most real-time processing, in most stream processing scenarios, the input is out of order. So data generated on different source devices can actually arrive at the system in a different order. That means data from, for example, data from 956 can actually come after the data from 958 and 1001. So that means even if we see this red block data from 1001, that doesn't mean we cannot simply say that the event time has reached 1001. That means all the data before 10 o'clock should already be processed. We cannot say that. Then how do we measure the event time in Flink? Well, the answer is watermark. Watermark is some kind of signal that we inserted into data streams to indicate the progress of the event time. And a watermark T represents that the event time has reached out to T. It also means that we are not expecting more data with the event time earlier than T. Well, Flink provides many built-in strategies for generating watermarks. And also, we also support users to define their own strategies. For example, we can have a strategy like we just periodically generating watermarks with the max timestamp that being observed minus some certain some fixed time. Well, unfortunately, in most of the real-time scenarios, the data lateness cannot be avoided. So some records may violate the watermark semantics. That means we may still receive data with earlier timestamp even after receiving the watermark. And users don't always want to sacrifice the real-timeness of the processing by waiting for the late data for a long time. So Flink provides various ways to handle this late data. For example, we can just drop the late data, we choose to ignore them, or we can send the late data to a side output for some special handling, or we can just update a result that has already been emitted. So this is how time-based processing is done by Flink. Well, this is the content that I bring today, and thank you for listening. So I'd like to see if there's any questions. Okay.
Can we give a big round of applause for Mr. Xintong Song?